Hello, my name is Shahriyar Shahriyari, and this is a lecture in a series of lectures on introductory operations research based on my book, Linear Programming, Duality, and Games. The subject of this lecture is linear programs in standard form. Linear programming is about maximizing or minimizing a linear function, which we call an objective function, subject to linear constraints, often linear inequalities. For example, maximize 7x1 plus 4x2 plus 2x3 subject to these conditions. Things like 4x1 plus 6x2 plus x3 less than or equal to 6, and also sign constraints, things like x1 and x2 and x3 being greater or equal to 0. In this lecture, we will tell you what the standard form of an LP is and introduce slack and surplus variables, and tell you what to do with unconstrained variables if your original LP is not in standard form. Let me remind you of some linear programming vocabulary. When we have something like maximize 4x1 plus 3x2 plus 2x3, x1, x2, and x3, the variables, the ones that we're looking for, are called decision variables. The thing we're trying to maximize or minimize is called the objective function. Then we have certain constraints. Functionality constraints give us relations between the different variables, and sign constraints define the range of the variables. Sometimes there's a little bit of gray area. So for example, when you have x3 less than or equal to 5, depending on the problem, that might be a functionality constraint. So this is an LP, but it's not in standard form. A feasible solution for this LP would be values for the decision variables that satisfy all the constraints. And an optimal solution would be the best one among all those feasible solutions, the best one that maximizes that objective function. Now I'm going to tell you what a standard form for a linear optimization problem is. A linear optimization problem is in standard form if all functionality constraints are equalities, there are no inequalities. All sign constraints are the form x greater or equal to 0. For every decision variable, the range is x greater or equal to 0. And we want the objective to be minimize a linear function. Two optimization problems are equivalent if feasible solutions and optimal solutions correspond to each other. This correspondence doesn't have to be necessarily one-to-one, but it has to be that in this optimization problem, if you have a feasible solution, you know which feasible solutions in the other one corresponds to, and vice versa. And you should also be able to know that if you have an optimal solution here, that corresponds to an optimal solution over there, and vice versa, so that you can go back and forth. If you have two optimization problems that are equivalent, you could solve one or the other, and from that, you could get the answer to the other one. And we will have a definition now for what a linear program is. I've been using the word linear program, but I've not really been defining it. A linear program is any optimization problem that's equivalent to one in standard form. If you can translate your linear optimization problem into one in standard form, then that's called a linear program. Therefore, if you know how to solve linear programs in standard form, we will be able to solve all these other linear optimization problems that are equivalent to them. So through an example, I'll show you how we get a optimization problem into standard form, if it's possible to do so. For example, here we have this problem, maximize 4x1 plus 3x2 plus 2x3, subject to these conditions, and it's definitely not in standard form. To start with, we want to change that maximization problem into a minimization problem. That's very easy to do. All you do is multiply by a negative. Maximizing 4x1 plus 3x2 plus 2x3 is the same as minimizing minus 4x1 minus 3x2 minus 2x3, so nothing has changed there. What do we do with x1 minus 3x2 plus x3 less than or equal to 5? We add an x4 to it and make it x1 minus 3x2 plus x3 plus x4 equals 5, where x4 is a new decision variable and it's greater or equal to 0. It's a variable that will pick up the slack in that equation, and it's called a slack variable. If you solve this original problem and found values for x1, x2, and x3 that would satisfy this equation, x1 minus 3x2 plus x3 less than or equal to 5, then x1 minus 3x2 plus x3 would be a number less than or equal to 5. And whatever it is, you could add something to it and make it 5. So if this was 4, then x4 would be 1. If this was 5, then x4 would be 0. And as long as you make x4 greater or equal to 0, then the converse is also true. If you find a solution that satisfies this equation, x1 minus 3x2 plus x3 plus x4 equals 5, and x4 is greater or equal to 0, then that would mean that x1 minus 3x2 plus x3 is also less than or equal to 5. So we haven't lost anything. We've added a dimension to our problem, but we haven't lost anything in terms of feasible or optimal solutions. What do I do with the other one, 3x1 plus 2x2 greater or equal to 3? I do something similar. I can't add a variable, I'll subtract a variable. Remember, I want all the new variables that I introduce to be greater or equal to 0, because that's one of the conditions for standard form. And again, if you solve the original problem and find x1 and x2 that give you 3x1 plus 2x2, a number that's greater or equal to 3, then in the background is also this x5 telling you how much you were off, how much you were greater than the 3. This new decision variable is called a surplus variable. And what do I do with x1 being less than or equal to 0? I just change variables. Instead of x1, I'll put y1. What's y1? y1 is minus x1, so x1 is minus y1. And if x1 is less than or equal to 0, then y1 will be greater or equal to 0. So everywhere in the problem, wherever I see an x1, I will put a minus y1. So let's see where we're at. We had this original optimization problem and we made some switches. So far, we have a minimization problem. We changed all the signs to negative. The y1 here has a plus because remember, we changed every x1 into a minus y1. So we first put a minus in front of all of these, but then that minus x1 became y1. And everywhere we saw x1, we're replacing it with minus y1. We have our slack variable and surplus variable. These new two variables, x4 and x5, are greater or equal to 0, and y1 is greater or equal to 0. We still have work to do, but we're getting close to where we want to be. So now, what do we do with x3 where it's between 2 and 5? So when we see that it's greater or equal to 2, we do another replacement. Instead of x3, we put y3. What's y3? y3 is x3 minus 2. x3 is between 2 and 5, then that means y3 is between 0 and 3. So y3 is greater or equal to 0, which is what we want. y3 less than or equal to 3, that will be a new functionality constraint. Everywhere we see x3, we're going to replace it with y3 plus 2. In the objective function, I actually don't need to put y3 plus 2, because if I put y3 plus 2, I'll get minimize some linear combination of x1, of y1, x2, and y3, but then with a constant. And that constant is not going to really matter. If you minimize something minus 4, it doesn't matter if you have that minus 4 in there or not. So in the objective function, I'm going to just replace x3 with y3 just to keep things neater. So the conditions that we'll have is y3 is greater or equal to 0 and y3 is less than or equal to 3. Now y3 less than or equal to 3 is a new functionality constraint, and I need for that to be equality, so I need to add another slack variable and replace y3 less than or equal to 3 with y3 plus x6 equals 3. Let's see where we are now. Previously, we had got to this linear optimization problem, and now we are changing x3s to y3 plus 2. When we do that, this is the new optimization problem we get. We have a new functionality constraint and a new slack variable. All of y1, y3, x4, x5, and x6 are all greater or equal to 0. I do not have any x3s anymore. I have y3s. I've changed x3s into y3 plus 2, except in the objective function, I've taken the liberty to drop that constant because it doesn't change anything in terms of minimizing the objective function. The objective function over there and here will have different values, but minimizing this one and that one are not any different. The only thing that remains to do is to deal with x2. x2 doesn't have any constraints. Its range is from minus infinity to infinity. It could be negative, 0, or positive. And that's not allowed in a standard program. So what do? One way to deal with that is to go in one of the functionality constraints and solve for x2, and then substitute and eliminate x2 from all the other ones. So solve in this one what x2 is, and then plug it into all the other ones, and then you don't have x2 anymore. That's one way of dealing with it. The other more preferred method is to introduce yet another two variables, x2 plus and x2 minus, both of which are greater or equal to 0. x2 is going to be x2 plus minus x2 minus. These two greater or equal to 0 variables allow us, by subtracting them, to make x2 be anything we want, positive or negative. If you want x2 negative 3, then I will make x2 plus to be 0 and x2 minus to be 3. I could also make x2 plus to be 1 and x2 minus to be 4. I would have actually a lot of choices to come up with minus 3. I could also come up with 3. x2 plus is 3 and x2 minus is 0. Vice versa, if you have non-negative values for these two, then you will know exactly what x2 is. As long as x2 is equal to x2 plus minus x2 minus everywhere, making that change is not going to change anything in terms of the conditions or the objective function. So originally, our optimization problem was this guy. For x1 plus 3x2 plus 2x3 was the thing that we wanted to maximize, and we had functionality constraints and sign constraints. Previously, we switched it to this problem where everything was fixed other than x2, and now by replacing x2 with x2 plus minus x2 minus, we are in standard form. So how do I know I'm in standard form? First of all, I'm minimizing a linear combination of my variables. The constraints, the functionality constraints are all equalities. They're all linear equations and they're all equalities. and every single one of my variables has the range greater or equal to 0. Note that instead of 3 variables, now we have 7 variables. So in some ways, we have made the problem more complicated. On the other hand, we haven't really changed anything. And especially theoretically, this helps quite a bit to have a standard form for talking about linear programs. So let me recap. The standard form of a linear program is the minimization problem. The objective is to minimize a linear function, and all functionality constraints are linear equalities. For each decision variable x, the sign constraint is of the form x greater or equal to 0. Not all optimization problems can be modified into the standard form. Sometimes some clever manipulations will turn things that you might not think of as linear optimization problems into linear ones. I've shown you some of the things you can do, but I certainly have not shown you what all the possibilities are for turning an optimization problem into standard form. But our main point is that what we mean by a linear program is any optimization problem equivalent to one in standard form. For example, if you have one where the variable is x greater than 0, then that's not a linear program. That changes the problem considerably and will not be in standard form. In the upcoming lectures, we will almost always start with a linear program in standard form. This is the end of this lecture. Like my video if you liked it. Subscribe to my channel if you want to be subjected to more math videos on your feed. Keep hydrated at all times. Leave a comment if you can. Tell me where you are watching this video from and what makes you want to watch math videos.